In the last module, we introduced ourselves to time series analysis, and we saw that broadly time series analysis can be classified into two types of studies. One was the time domain approach and the other was the frequency domain approach. Now, we will be concentrating primarily on the time domain approach, and in today's lecture we will be looking at in details at the time domain approach. Now, the time domain approach basically can be classified again into three types of models. So, one of the models is the old classical model that was previously used, but after that the Box-Jenkins model came into vogue, and the Box-Jenkins model are currently very popular and very widely used. Then we also have what are referred to as the volatility models. This began with Engel in 1982, and this accounts for the variability in the model. So, there are different types of models that we can look at. In today's lecture, we will be concentrating on the classical models, and in particular we will be looking at the estimation of the trend and the seasonality in a time series. We will look at analysis in the time domain. Now, time domain studies can be broadly divided into the classical models, the Box-Jenkins models and the volatility models. Not that the three are mutually exclusive, a study can involve all three simultaneously, particularly the volatility models with the classical or the Box-Jenkins model, because the volatility models are primarily the modeling of the variance, where the classical models and the Box-Jenkins models are modeling of the mean. So, you need to combine the volatility models with the classical or the Box-Jenkins models. But these are three distinct studies, and there had been very extensive studies in all three of these branches. So, we will look at these three branches separately. The components of a time series are primarily stationarity and evolutionary. So, we will say that x t is stationary and we will denote by E t the evolutionary component. What is stationarity? It means the time series does not evolve over time. It moves with time, but does not change in the mean and variance with time. So, there is no change in the mean and the variability with time. There would be a random component always involved, but that does not change the basic structure of the series. On the other hand, we have a evolutionary component. This evolves over time, that is, the mean and variance changes with time. So, the time series looks different when we plot it at different time points. So, it keeps on changing the structure as we move along over time. The two most important components of the evolutionary part are the trend and the seasonality. We will denote trend by T and seasonality by S. So, the structure of a time series. Usually, if you have a additive model, we have y t is equal to t t plus s t plus x t. So, t t and s t consist of the evolutionary part, whereas x t is the stationary part. On the other hand, we can have a multiplicative model where we have y t is equal to t t into s t into x t. Generally, a multiplicative model with a log transformation is used, which reduces the model to an additive one. So, most time series we generally start with a multiplicative model, then take a log, and hence the log model now is a additive model. Actually, if we have a exponentially increasing trend, then the log actually reduces it to manageable limits. Let's look at the evolutionary component in a additive model. So, we have yt is tt plus st plus xt, and the evolutionary component is the trend and the seasonality component. What is trend? Trend is a smooth long-term movement of the time series, as opposed to seasonality, which is a cyclical movement with period less than a year. So, let us look at an example. A particular shop is increasing its sales over the years. We will call this a trend, an increasing trend for the sales of the particular commodities of that the shop actually sells. But then if you look at the monthly data of sales for this same shop, what you see is that in particular months of the year, the sales are high, particularly during the festive seasons, and then the sales are low in certain other months. These sort of movement are referred to as seasonality in time series. We will be looking at this a few more examples, but before that, let us explain one other movement that is often talked about in the classical model, and that is a cyclical component. Now, cyclical movements are movements which are like seasonality. Obviously, it is cyclical, but it has periods greater than a year, and hence we do not treat them as a seasonal component. And these are the highs and lows that the businesses have over the years, but this can very often be incorporated into either the trend or the stationary component, and hence in our model we will not be looking at cyclical component separately. The original classical models had a cyclical component, but later on this were either incorporated with the trend or with the stationary part of the model. This is what a trend would look like. This is the data of population in thousands over the decennial censuses. So, the data starts from 1790 and ends at 1970, and we can see that the population is increasing with time over these years. So, we will say that there is a trend, increasing trend of population over the years for this particular country or for this particular data. As opposed to this, this is the daily maximum temperature in Melbourne in Australia between 1981 and 1990, and you will see that the maximum temperature has a cyclical structure. This is because in Australia, where you have the winter during the months of May, June, July and August, the maximum temperature would be low, whereas during the summer months of November, December, January, February, the maximum temperature would be much higher. So, if you look at this structure and if you are looking at daily temperatures, so daily temperatures in the last few months or the first few months of the year, that is November to February, would be much higher, and the months of May, June, July and August would have a very low temperature. So, every year this is repeated, and hence over the years you get a cyclical structure for the data. Now, let us look at trend, and let us see how we can estimate trend by the classical method. So, what is trend? The trend is a slow long term movement of a series. It can be increasing, it can be decreasing with time, and it can also take various other shapes. For example, it can increase initially and then reach a peak and then start declining, or it can be exponentially increasing or exponentially decreasing. So, there are various types of trend functions that we can be looking at. The methods of estimating trend are primarily two. One of them is the mathematically curve fitting and the other is the moving average method. There are several other methods, but these are not as popular as these two methods. Now, what are these two methods? Before we come to that, let us have another look at what trend is like. This is again an increasing trend and this is the population over the years as we saw before. So, how do you estimate this trend lines? You have the values of the population at different time points and you need to find a smooth curve that passes through these points or passes close through these points which can be used for prediction purposes for subsequent years. Let us look at method of curve fitting. As is obvious from the last graph, we can use some mathematical function. What sort of mathematical function? The simplest of the mathematical functions is a linear function. So, the trend t is given by a plus bt. Of course, if b is positive, we have a increasing trend. If b is negative, we have a decreasing trend. And you can see that if b is equal to 0, then the time series or the trend part at least remains constant at the level a. Very often, as I said, that it may not be a linear function, it can be a quadratic function. So, again it can be increasing or decreasing and you can have a maxima and a minima, and therefore, there may be a turning point in the trend and we can account that for by a quadratic function. To generalize this, we can have a trend which is a mth degree polynomial. So, the first two are special cases with m equal to 1 and m equal to 2. As opposed to this, we can have an exponential or a modified exponential trend curve. We can have a logistic trend curve. So, there are various types of mathematical curves that we can use. Most of these curves can be estimated by the least squares method. By estimating the curve, what we mean is to estimate the parameters of the curve. For example, if you are looking at the quadratic trend, we need to know what A, B and C is like, so that we know the trend curve, and if we are given a particular value of small t, we can say what the capital T trend value is like. So, this can be done by minimizing summation of y t minus a minus b t minus b m t to the power of m square with respect to the a's and the b's. So, this is one way of estimating the parameters. Very often there are other techniques which are used, because the least squares may not be so simple to compute when you are looking at the exponential or particularly the logistic curve. So, there are different methods like 3-point averages and other such methods by which we can estimate the parameters. So, we are not going to discuss in detail the parameter estimation here, but most of the polynomial curves can be estimated using the least squares method. So, this is how we can get trend by the method of curve fitting. As opposed to this, we have what is referred to as the moving average method. It is very often said to be a linear filter, where we use a weighted local mean. What does this mean? It means that we take a weighted average of the y's. Suppose we are looking at yt and we have decided that we will take a weighted average of the previous g values of y and the subsequent m values of y. So, Tt would be an average of this y values. What it does is basically when you average out the y values, it actually excludes the noise and it gives you the slow moving structure of the time series. So, that is why we can take a local weighted mean as a representative of the xt value, which would actually erase out any other fluctuations involved. Usually we take g equal to m and then we have a symmetric weighting system. So, we have suppose m subsequent values and m previous values and of course, the current value itself. We refer to this as a simple moving average if all the coefficients A are equal to 1 by twice m plus 1, and in that case the trend value looks like the sum of the previous m plus the subsequent m plus the current value. So, there is a total of 2m plus 1 values. So, this sum is divided by 2m plus 1 to get a representative value of Tt. You can see that when you average this out, all the fluctuations that you have in the adjacent values of Yt are actually erased out. Once we have found trend either by the curve fitting method or by the moving average method, we can remove it simply by subtracting it from the original series. So, Yt minus Tt, we will call this dTt, and this is equal to the seasonality plus the xt component. So, what we now have is a detrended series which only has seasonality and the xt part. So, it is a series without trend. An alternative way of removing trend is by differencing. So, if you have a series Yt, then Yt minus 1 is the first difference. You can take a second difference which is the first difference of the first differences, and this way you can also remove trend. This is easy to see and you can do this in practice. You can try this out, you use the linear trend and you take the difference of Yt minus 1 and you will see that the trend factor actually is taken out. Similarly, if you have a quadratic trend, then take the second difference and the second difference in that case, the first difference would not do in that case, the second difference would take out the quadratic trend. So, depending on the structure of the polynomial, if you have a mth degree polynomial, you need a mth degree difference to remove the trend part and get a detrended series. Now, once we have the detrended series, we can look at the seasonal component. This is a cyclical periodic movement with period less than 1 year. So, if you have quarterly data, you can have a quarterly seasonality. If you have monthly data, you can have monthly seasonality. If you have daily data, it may be a weekly seasonality. So, seasonality can be of different periods. So, it may be weekly, it may be monthly, it may be daily, it may be hourly even. Now, the methods of estimation of the seasonal component are primarily the difference to trend method and the difference to moving average method. Actually, the two methods are the same and the two names comes in because of the way that we have actually estimated trend. So, if we have estimated trend using the curve fitting, we have the difference to trend method. If we have estimated the trend using the moving average method, then we have difference to moving average method. This is how the seasonality looks like, and you can see that for each season we have a particular seasonal component. So, in some seasons the seasonal component is high, in some seasons it is low, and we want to find out in which of this, if this is monthly data, which of the months the seasonality is high and which of the months it is low. So, it is not going to be over years, it is only a seasonal component value for each of the months in this case. How do you estimate seasonality? In the original series xt we had trend, and yt minus tt gives us the detrended series. Treat the xt in this case as some random noise. For each season there is a single seasonal value, so that if we have h period seasons, that is in case of weeks it will be h equal to 7, in case of months it will be h equal to 12, for quarterly data it should be equal to 4, then obviously for each of the years the seasonal component would be the same. So what we mean by this is that the seasonal component of July in 2015 would be the same as the seasonal component of July in 2014 or 2013, etc. But it will be different from the seasonal component of August in 2015, which again would be the same with the seasonal component of August in 2014 or 2013, etc. So for each season we have a different component which remains unchanged over the years. Each season what we do is we average over the different years to eliminate the noise xt. So what we get from the difference to trend or the difference to moving average, this should have been the same, but there would be the noise caused by xt. So what we do is we average the st's out over the year, so that the noise is actually averaged out. So this is a more general formula. So we are going to average the values over all possible seasons, particularly for that or for a particular season over the different years. And then what we do usually is to adjust the averages, so that the sum of all the seasons averages is 0. So generally there would be some errors due to calculations or some approximations, and hence the sum might not come out to be 0, but the average should be adjusted to 0, so that you know that if you have a positive value, then it's above the average generally, and if it's a negative value, then it's below the average value. Okay. This gives the seasonal effects st, and when you have got the seasonal effects and you use those, then you get a much smoother curve like this. So what we have is, when you have got the seasonal values, we can remove, like the trend, the season effects as well, and we can get a detrended deseasonalized model. We will call this dt, which is dtt minus st, which is the detrended series minus now the seasonality, and which actually gives us the xt series itself. So dt or xt is a series without trend and seasonality. We can expect a detrended deseasonalized series to be mean stationary. We will look at what mean stationary really means, but we can expect this not to evolve too much over time. So the evolutionary part is excluded from xt. There is an alternative method of detrending and deseasonalizing a series, and that is by differencing. First, difference to remove the trend. We have seen this before. So if you take yt minus 1, that is the first difference, then if you have a linear trend, then that is removed. And if you have higher degree trends, then you can remove it by higher degree differencing. Let's keep this simple for the timing. Let's look at the first difference and we remove the trend, and then we can remove the seasonality by appropriately taking a difference. In this case, a difference of order s, which is the order of the season. So delta yt this year minus delta yt minus s last year, that is the July value this year minus the July value last year, would, mind you, these two values are going to be same. So if you take the difference of this is going to be 0, and this would be actually removing the seasonal part as well. So differencing is another way of removing both seasonality and trend. Both differencing can involve higher order differences depending on what the structure of the trend or the that we have. Began today's lecture by looking at different types of models that we can have when we are studying a time series through a time domain approach. These are the classical models, the Box-Jenkins models, and the volatility models. In today's lecture, we had been primarily concerned with the classical model. We saw how we can estimate trend and how we can estimate seasonality. These are the two prime components of the evolutionary part of a time series. Once we have removed these parts, generally a time series reduces to a stationary component. Of course, there would be some non-stationarity in the variance, but usually the main non-stationary components as looked upon from the classical point of view are through the trend and the seasonality. So, we have seen how we can estimate trend and seasonality and then detrend and deseasonalize particular time series.